somebody would make, and I would understand this mistake, is that somebody might, on part A, they might change the standard deviation. They would do this here. It's not time for that yet on part A. Why would somebody do that? Because they see the 280 quarters. But I didn't take a sample and ask a question about the sample mean until part B. Do you guys see that? Part B asks a question about the mean. What's the probability that the mean, blah, blah, blah. Part A just says, all right, what if I put 280 in there? How many would be rejected? So part A, I just want to find the probability that a quarter is between, actually I want to be rejected, right? Yep. So if I find the probability that it's between these two, that's the probability that the quarter would be what? The machine, what would happen if I put a quarter in there that's between those two? It would accept it. So if I find that probability, what's the probability it would reject it? 1 minus that, right? The opposite. Cool. Now, why do I not have to do the change of standard deviation? Because it's not asking for a probability of all 280 quarters being rejected, is it? It's asking for the probability that, not the probability, but it's asking for the expected number of 280 quarters that would be rejected. So what's the probability that any quarter is rejected? Single quarter. And then that, I think that percentage of 280, that's how many I would expect to be rejected. So part A is really this, and part B is going to be, and they pretty much spell this out for you, that. And that's all I need. That's the only difference I need right there. That's the one. I've got to change the standard deviation because now they're asking a question about the sample mean. So now you know why I said the trigger the way I did. How do I know when to change standard deviation? When they take a sample and they ask a question about the sample mean. They didn't ask a question about the sample mean on part A. They just asked how many out of 280 would you expect to be rejected, right? So how do I do this first, this part A one? This is just a regular old classic z-score problem. Draw the picture, what's right in the middle? So 5.67 right in the middle. Here's my 555, here's my 579. I want this area, I actually want this area out here, right? I truly want to know what the rejection area is. So you could do that one directly, or my suggestion would be to find this area and then take 1 minus that. I mean, either way, it's about the same amount of work. So let's find that area first. Let's just do that. Now, the problem with this problem is, and this is not a problem, this is just real life. I mean, that's the question in real life, or close to it. We have to convert it to a question that we can then represent on a picture, and then we can do our work to it, right? I mean, that is the problem. Math is not written in English because it's got to work within itself. We have to convert any English problem into a math problem before we can attack it. So part A is just change those to z-scores, look them up, subtract the areas, right? Because I want the area between. Anytime I want the area between, I want to subtract areas to get what's left. So convert each one of these to a z-score. I saw a few little problems like people, the mean never comes first. It's always your data point minus the mean. I had people turning it around, which will change the sign of the z-score. What would I expect about the z-score of this? It's going to have to be negative, exactly. So it should surprise you if it's not. You should go, oh, shit, what the hell? It should be negative. Yeah, sounds about right. Negative. And then the z-score for the other guy, 5.79. Not surprisingly, it's just positive 1.94, right? It's not surprising because they just made this, what's right in the middle of that one, the expected number. And then they just kind of had a tolerance built in, give or take this much. So how do you find the area that's here? Yep. So look up this area here for the 1.94 minus this area here. Or some of you guys might realize that's not really answering the question. You still have to do 1 minus that area to answer the question. You could just look up this area here, look up this area here, and do 1 minus it to get the area up there. Because they want the probability I rejected. When would I be rejected? When my quarter is too weird. And what's weird in this case? Out here.
Say that again.
The work that I have drawn up here. Once I get this area, I still have to do 1 minus this. Because this is the probability that a quarter is accepted. And they want rejected, right? You could, instead of doing this work, you could just get this area and add it to this area. And the funny thing is, I mean, aren't these both 1.94, negative 1.94? So what's true about this area and this area? What should be true about those two areas since these are the same distance on both sides? They should be the same. It's symmetric, right? This should be the same as that. So the exceptionally funny thing about this problem is if you look up negative 1.94, get an area, double the damn thing. That'll be the probability of rejection. That'll be the area that's on the outside here. There's a nice big acceptance range. What's probably somebody's rejected that's out there. And they always have to kind of fine-tune it. How many people do I want writing and complaining to me versus how many people do I want give me slugs and getting actual food? You guys, do they still call it slugs nowadays? Or do they even still do that? Have our machines gotten Intel? You know the one? Have you ever seen those? They're just little things of metal.
Washers.
Washers, or yeah, discs, right? And they used to work really well because the machines used to be really stupid. I think they're getting pretty damn smart nowadays. They're able to scan stuff and so forth. I don't know.
Real quick. So then after we get like the 0.9476, which is in between.
Okay, so you got 0.9476. 1 minus that is?
Gives us the outside.
Probability of rejection is 1 minus acceptance.
0.0524.
0.0524. So what is that now? What is that? 5% what?
Rejection.
So 5% of all quarters should be rejected. So if I put 280 quarters in there, how many should I expect to be rejected?
5%.
Yeah, that times 0.0524. That'll be the answer for part A. So part A, the whole thing with part A, you see that expected number. That should make you think about NP. Isn't that the expected number? So what is this P though? That would be the probability of rejected quarter. We first had to figure out what that probability was before I can multiply it by how many quarters I was going to try to see how many are going to be rejected. Right? I can't do this formula until I have a probability. And what is that probability? The probability of rejection. That's the chances that my quarter will be rejected. Or the percentage of all quarters that would be rejected.
The 280, what are you multiplying that
By the 0.0524. Man,
by? Okay,
so that's here, right? It'd be 280 times the probability of success. In this case, the success would be a rejected quarter. So that would be the expected number of rejected quarters. So to take a step outside of this problem real quick, they can set this tolerance level in the machine. This is true quarters, right? This is the standard deviation on quarters, period. So these are real quarters. They just are quarters that were really worn down or that the machines didn't make correctly or whatever. And these are also real quarters. They just cut it too wrong, cut a little too much metal off. These are true quarters. So of course I'm going to be upset if my real quarter gets rejected, right? If you see those commercials, the dollar bill, you know, I'm going to be upset. So they can control the percentage of people that will be pissed off at them because their quarters get rejected. But if they put this probability too far down, then they're getting more and more people that might be giving me fake money, right? So they got to kind of balance those two things. And you can't possibly balance those two things unless you're able to do this kind of analysis. This analysis tells me, well, where can I set things so that I'll be happy, so that people will be happy? Get off my back and leave me alone about my machine. Yeah.
How did you get 0.9477?
Somebody did the work and gave it to me, but hopefully that's right. So look up negative 1.94, right? Negative 1.94. What area do you get for that? 0262?
Yeah, you get 0.9477.
Okay, and then you just subtract those two to get the area in the middle, right? Okay. That's the only number I heard coming out from you guys, so that's the one I used. You can double check it. Now, what would be the difference with part B?
So then with that, you have to get, that's when you
Yes.
have to do that.
They're asking me a question. They're very specific about it. If you look at part B, they say, what's the probability out of 280 that the mean of those 280? Okay, crap. They took a sample, 280, and they're asking me about the mean. I've got to change the standard deviation. Then you would do the same thing we just did, but just with the new standard deviation that I would get.
And then you don't have to do the 280 times whatever you're getting. You're just getting the one.
Yeah, part B is just a probability period. Yeah.
Okay.
Part B is a probability period. Cool. Yes?
I have a question for 6QB. How did you get 5?
Oh, 6.2. How did I get where? Oh, okay. Well, part B is also, again, this comes out of section 6.6, but I don't know if I really want to give you the full thing, but it's maybe a little too much to try to do now, but if the mean is too small, let's say I got 0 through 14 like I did on that one piece of paper, up to 14, right? So let's say the probability is like 0.01, then the mean would be 0.01 times 14 is 0.14, right? So that would mean the most likely thing would be 0.14, so my picture would look like this. Cool? Do you kind of get what I'm saying?
Yeah.
For a binomial, the most likely thing should be the mean. So if this is if P is 0.01 and I got 14 things, the mean is 0.14. So that would be the tallest bar. Could this possibly be normal? No. Why not? I didn't give it room to go up and come back down. So if NP is at least 5, that's what that says. If NP is at least 5, I'm giving it room to go up and come back down. Now NQ is just on the other side, really. It just says the most successes, the most failures has got to be, the least failures got to be 5, so it kind of keeps it in the middle. But again, that's another one that's from 6.6. We didn't cover that in class. That's why it sounds unfamiliar. It should.
But it's going to be on your
No. I just forgot to say that part won't be on there either. I mean, that's from 6.6. But like I said before, I said that handout I gave you with the histogram in the middle of the paper, tossing a coin a few times. I said this looks normal. Later, we're going to have a more technical way to find out if something's normal. Well, here it is. NP and NQ have to be bigger than 5. If that's true, then a binomial is approximately normal. And that's really all there is. If the mean is too small, it doesn't have room to go up and come back down. How could it possibly be bell-shaped then? It's got to be about 5 for it to have room to go up and come back down. And it can slam into the other side too if I don't make NQ greater than 5. It's got to keep it in the middle. So it can go up and go back down. It's very simple. Yeah.
Back to 18 for B. I did
It is
that-
because I say it is, though.
After I do the standard deviation, like the new standard deviation,
So for part B, yeah.
I'm getting like the answer for the new z-score is negative 30 and 30.
Yes, I love it.
So
Because I got such a huge sample, 280. the standard deviation is going to be silly.